Hi everyone, this is Konstantinos, and together with Park, we will be talking to you today about the end-to-end optimization of machine learning prediction queries. This is work done at Microsoft's Gray Systems Lab. As most of you are already familiar with, machine learning involves two main parts. The training part, where we're using existing data to build models, and the model inference part, where we're using these trained models in order to perform predictions over new data. Now, 2 years ago at Cider, we laid out our vision for enterprise-grade machine learning and identified various challenges across the board. In this work specifically, we will be focusing on the model inference side of things. And to make things a bit more concrete, let's consider the following scenario. Let's say we're a hospital, and every morning we want to find the patients with asthma who are at high risk of developing some COVID-19 complication. In order to run this query, we're going to be using this model that has been trained over data throughout the country to find the risk of a patient for a COVID-19 complication. And we will embed this query in a bigger SQL query that looks as follows. So the upper part of the query identifies the data that will be used for inference. So you can see there we have this three-way join with the patient information and various tests from the patients. Then in the second part of the SQL query, we have this predict statement that uses this trained model over the inference data to do the predictions, and then on top of that applies various filters for asthma and risk of COVID. Don't worry too much about the specific syntax. The point is that we're using SQL here because it's prominent in the enterprise, and similar offerings from Google and Amazon are using a similar syntax as the one we follow in our engines. Now, the question we want to answer in this work is, how can we optimize such queries holistically? So not just optimize the data part or the machine learning part, but look at the query as a whole. And as you will see throughout the talk, we managed to have some very considerable speed ups by doing our optimizations, both against our plan, both on top of Spark and SQL Server, with up to 330 times faster queries, and also considerable speed ups over GPUs and orders of magnitude improvements over state-of-the-art solutions. Now, to motivate a bit some of the specifics of our work, first of all, we focus on inference here. The reason is that inference drives the cost of machine learning in the enterprise. Yes, you are all aware of huge clusters with tens of thousands of GPUs that are used to train models, but the point is that these models are trained once, but then are used millions and millions of times to do predictions. And actually the industry is going towards even pre-trained models that are hosted in the cloud and can be used by anyone. So as per various estimates, more than 80% of the cost in the enterprise and in various companies goes towards machine learning inference, and even up to 90% of the cost is dedicated to that. Moreover, batch inference is very important. This is as opposed to live inference that cares about millisecond latencies. Here we can do inference at regular intervals. In 130 customer engagements, we found that actually 91% of the use cases were batch use cases, and another 6% of them could be covered by doing batch at short intervals. The third point is that we're focusing on prediction queries that involve traditional machine learning models. That is your linear and logistic regression, tree models, or decision trees, random forest, featureization operators, and so on, because those are the most widely used over structured data. And we have backed this observation by various Kaggle surveys, as well as a big analysis of more than 10 million GitHub notebooks that are publicly available. Some more thoughts. We turn to the trained pipelines, and we want to see how complex they are, to see whether it's worth optimizing and in which ways. So we analyzed more than 500 scikit-learn pipelines over OpenML datasets. Here I give various features from our analysis, but I want you to focus on some key takeaways. First of all, it's not possible to manually optimize these queries because the trained models are really complex. They involve, on average, more than 120 operators, and some can have even more than 3,500 operators. Second, we cannot have a one-size-fits-all optimization because these models vary widely. So we can have some models that have on average 77 input features, but there are models that have more than 50 million input features. So one could think that we could translate everything to SQL, but with this many input features, no reasonable SQL query could be efficient. And third, we identified various untapped opportunities. For example, we saw that almost half of the features that are used in these models remain unused during inference. And this is because of the way training happens, as we identify more in our paper. Let's see how our system Raven, our optimizer for prediction queries in Azure data, looks like from above. So we have as input our data and our prediction queries that involve data and machine learning operators. We're going to execute them on top of our engines. I'm not going to give you more specific details about the execution, but essentially keep in mind that we have put a lot of effort in order to enable our machine learning runtimes to be executed, to be collocated with our data engines, namely Spark and SQL Server. But the focus here is on optimization. So the main idea is that we use a unified intermediate representation to represent both the data and the machine learning operations in the same structure. We give that as input to our optimizer, and then we optimize the plan as a whole. We spit out an optimized intermediate representation which we're then going to execute. Park is going to talk in a minute about the types of optimizations that Raven enables, namely logical and logical to physical optimizations. But let me very briefly talk about the unified IR. The IR of the query we described in the beginning of the talk looks as follows. As you can see, it includes various relational algebra operations, but also it has machine learning operators. So we have relational algebra, we have linear algebra, and we have some other machine learning operators that cannot be expressed using linear algebra, as well as various data featureizers. You can find more details in the paper about our IR. Some important design decisions, though, to keep in mind in order to make our IR and our system as a whole applicable to various enterprise settings is that we started the IR from a machine learning IR, Onyx, which is open source and publicly available, and we added data operations on top of it. The reason we followed this rather than the other way around is because there are way more machine learning operators than relational algebra operators. So it was a much more feasible decision to do it this way. And now Park is going to be talking to you about all the optimizations.
Thank you, Konstantinos. Next, I'll briefly go over how Raven works with our running example. Here is an example prediction query that is to find asthma patients who are likely in the high-risk COVID-19 group. Given the unified IR, including both data and ML parts, Raven goes through two major steps. First step is to apply our novel logical optimizations. And the second step is called logical to physical runtime selection. Now let me double click the first logical optimization step. In this logical optimization step, we apply a set of cross optimizations by passing information across data processing part and ML part. The first cross optimization is called predicate-based model pruning. As you can see in this example, there is a predicate tells the patients have asthma. We can pull this information all the way up to ML tree model and prune the tree branches based on the predicate. Another cross optimization is model projection pushdown. This time we pass the information from ML model to data part. In this example, since patient's EPM column is no longer needed, therefore we can add an additional projection in the data part. Another logical optimization is called data-induced optimization, where we exploit statistics of the underlying data to further simplify the query plan by enabling cross-optimizations. These logical optimizations are always beneficial, and therefore they are applied first. This is similar to the heuristic optimizations that are always applied first by relational optimizers. The second step is called logical to physical optimizations, which aim to convert a set of operators to another in order to allow more efficient engines and hardware to be used for executing those operators. Raven supports two types of operation transformations. One is ML to SQL transformation, where we convert ML operators to equivalent relational ones. The main benefit of this conversion is to reduce or completely avoid invoking the ML runtime, thereby avoiding initialization cost and data conversion between the relational and ML engines. It can also enable more extensive relational optimizations in the DBMS, such as pushing ML computation below joins and aggregates. The other transformation is ML to DNN, where we translate traditional ML operators to equivalent DNNs that can be executed on highly efficient DNN engines like PyTorch, TensorFlow, and Onyx runtime. For this transformation, Raven leverages recent work on Hummingbird project from Microsoft. This is very important performance-wise, as DNN engines support out-of-the-box hardware acceleration through GPU's FPGAs. Most importantly, we observed that these logical to physical optimizations are not always beneficial. Blindly applying them can lead up to an order of magnitude slowdowns. Hence, Raven introduces optimization strategies to pick the rules that would lead to the best performance for each query on a given hardware setup. Instead of relying on hard-coded heuristics, Raven employs data-driven instance-optimized strategies. We have these three rule-based, regression-based, classification-based strategies. You can find more details about each of these strategies in the paper, but in summary, classification-based approach performed best in practice. We implemented Raven as an extension to Apache Spark, as described in this picture with the main Raven components in gray color. In particular, we introduced the predict statements to allow Spark SQL users to express prediction queries. And we added a new rule to the catalyst optimizer that internally invokes our Raven optimizer. Lastly, we defined the Python UDF that allows invoking external ML runtimes. Now let me share some of our performance numbers in Azure HDI Spark cluster. This graph shows the end-to-end prediction query time for two popular datasets for data science tests. One is credit card, and the other one is hospital dataset. In this graph, the red color is Raven, and other baseline ML runtimes are in different colors. Spark ML is in purple, scikit-learn is in blue, and Raven without any optimizations using Onyx runtime is in green. We used three different ML models, such as logistic regression, decision tree, and gradient boost models. As you can see, Raven cross-optimizations and transformations can give 2 orders of magnitude performance improvements over other state-of-the-art baselines. The next graph highlights that using GPUs can significantly decrease inference time, especially for complex models. As shown in this graph, for gradient boost models with a large number of estimators and deeper trees, Raven's ML to DNN transformation with GPU can give 8x speed up compared to the original model without transformation. To conclude, Raven is a prediction-ready system that is able to not only push information from relational operators into ML models and vice versa to holistically optimize prediction queries, but it can also pick the right target runtime. Novel Raven optimizer with logical optimizations and logical to physical runtime selection can improve the performance of prediction query by multiple orders of magnitude. Raven's extensible architecture enables us to easily add new optimizations as part of our future work. Thank you.